Okay, you want to understand Pascal's triangle binomial theorem in general term involving infinites on basis. So let's get it started. We understand this. You have a plus b to the power of 0 equals 1. Basically anything that's to the power of 1, equals 1. So we get that. And a plus b to the power of 1 is just, a plus b. And an a plus b squared, we take a plus b and multiply it by itself, right? So now you distribute, you go 1, 2. It's like kindergarten. It's like 1, 2. When it's 1, 2, right? Like I think like in, out, yeah, something like that. And you get that, and you get apes. Yep, you get the idea. So then you get like this triangle thing. You can see all the terms, all the coefficients. So you got a plus b. You can notice like you have the squares on either side. Like I don't have an a squared here. But I got double here. 2a, 3, right, 4, 4, and then I take all these coefficients and I'm gonna make a triangle. This is what they call as Pascal's triangle. So now I can like rewrite it like this because mathematicians make everything complicated. I don't know. And then this is the combinations formula. We can look at this in a minute, but you might notice some like permutations and combinations. But anyways, you put it out up here, and then you get this. And then so this is the equivalent statement of this Pascal's triangle. But we just write it out like combinations, and you'll see why in a minute. But remember, these are the coefficients of the a and b terms. And here's the combinations formula. So a choose b. And so what we want to think about here is that something I want you to notice is that this first row 0 0. Make sure you know that it starts at 0, and especially on this left hand this column. You'll see that it starts at 0 and then goes 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on and so on. Just make sure your column starts at 0, your row starts at 0. And then so you'll notice that A goes 1, 2, 3, that's your row, and then B is your column, right? We can try doing some practice problems if we want with this. I'd like you to sub in like these numbers and see if you can get this, just so you can kind of get a general understanding. It's fairly intuitive. We can even look at this. I want you to look at how Pascal's, we have a 1 on every side. You can just write this out and draw this, even if you want to. But I can like kind of prove to you. Let's look at this fifth row here. Right? So I plug in 5, I plug in 0 because remember this first column is 0, and I get a sum of 1. Here I get a sum of 5, right? And then here I get a sum of 10, right? And then all of them work out like that. It's really nice. And then yeah, so now I also want you to understand that like a squared and b squared, yeah. Why is it squared? What dictates these powers? And here I have a trinomial. I want you to or not, polynomial. You can look at this third row right here, right? We have like 3, 2, 3, and then like all of a sudden this a disappears right here. And you can kind of think of it like this, there's one term that'll exist when I distribute the a's. So a times a times a is a cubed, right? And then a times a, and then if I multiply by b, then it's a squared plus b. And that's how I get that kind of square, right? And in this one, now I only have one a because I can multiply by a and bb, right, when I expand. And in this one, I can even not have an a at all because I could just multiply all the b's, right? When it completely expands. So that's something to keep note of. Here's the general term formula. T equal is k plus 1, the term number. This dictates the term, right? So 1, 2, 3. Each term is this term. This would be term, I guess 0, right? Because it's k plus 1, right? And then so on and so on and so on. And then it's equal to this binomial here. This is what you're familiar with, like before we expand it. And here's written out in like a virgin mathematics way. And so what I want you to notice, right, is that, like I said, we this column right here is 0. So that's why we have a k plus 1, and it accounts for that. Something else that's interesting is that we see that this b is just to the power of k, because that makes sense, because this last row is going to be, a term doesn't exist, it's just b, and n minus k, well, because it's just the difference between n and k in finding these rows. I might clarify that later. This is Pascal's theorem. This is something that they taught me. They're like, oh yeah, you should memorize this. Again, this is just how Pascal's triangle works. I take 1 and 1 and I add, I get 2, right? And then so again, you think about it, I take this column, I add to that the column plus 1, column plus the other column plus 1 row, I get this. And it gives me the next column and row, the preceding one below it, right? So 3 plus 1 is 4, 6 plus 15 is 21. You could take any numbers, honestly, like 20 and 15 it gets 35, right? We understand that, I guess. And then this is just the power set. It just describes the sum of all binomial coefficients. What does that mean in non-virgin limit terms? Well, I have 1, 5, 10, 10, 5, and 1. And then let's say I add them up here. I did some quick maths. I think this adds up right. Yeah, I hope so. And you get 32, which is equal to 2 to the power 5. So if you think about it, this is in the fifth row. Like if I go back to the Pascal's triangle, right, the fifth row right here. And then so, 2 to the power 5 is 32, because that's the sum of it. I don't know, it might be useful for someone.
And then so sometimes in the case of some things that expand infinitely, this is like infinite series, right? You have in the case of whatever, you have in the case of 1 plus x to the power n. Where 1 must be this part must be 1, this must be x and to the power n, right? This forms an infinite series. It specifically happens when n is and then so you get the idea. And then so now it continues on, the series goes and it expands like this. And then so why does this happen, right? So we know the general form is let r equal 1, right? So this is going to be the second term because we plug it back in, tr plus 1. We go right here, right? So t2 equals n to the power, n choose 1, an minus 1, blah blah blah. And then remember, we're substituting 1 and x in because that's just our formula, right? What we're expanding. And then so let's put these values into our formula. We get something like this. A is 1, anything to the power of anything of 1, unless it's not, as long as it's not 0. It's just going to be that, right? So it kind of just disappears. It's just 1. It's like multiplying by 1. And then we can expand this choose, right? And so it becomes that. N factorial over n minus 1 factorial over 1 factorial, and then x to the power 1. These two cancel out. It simplifies n over 1 factorial times x, and then so we get that term. Yeah, see, term number 2 looks identical. Lovely. And then right here is the general term, n to the power, n times n minus 1, and over 1 n minus n times n minus 1 times n minus 2, n minus r plus 1 times x to the power r factorial.